by Paul Rinken, a mathematical discrepancy in the expansion rate of the universe is now pretty serious and could point the way to a major discovery in physics, says a Nobel laureate. Scientists have confirmed the expansion rate of the universe is accelerating, but are unable to say why. Photo 123RF. The most recent results suggest the inconsistency is not going away. Professor Adam Rees told BBC News that an unknown phenomenon, such as a new particle, might explain the deviation. The difference is found when comparing precise measurements of the rate obtained in different ways. However, the statistics are not yet at the threshold for claiming a discovery. Professor Rees, who is based at Johns Hopkins University in Baltimore, Maryland, was one of 3 scientists who shared the 2011 Nobel Prize in Physics for discovering that the expansion rate of the universe is accelerating. This phenomenon was widely attributed to a mysterious, unexplained dark energy filling the cosmos. Values holding the unit of measurement used to describe the expansion is called the Hubble constant, after 20th century astronomer Edwin Hubble, after whom the orbiting space observatory is named. Appropriately, Professor Rees has been using the Wide Field Camera 3 instrument on the Hubble telescope installed during the last servicing mission to the iconic observatory to help refine his measurements of the constant. The answer we get is 73.24. This is not very different to what people have gotten before measuring the Hubble constant. What is different is that the uncertainty has gotten quite a bit smaller, he said here at the 231st American Astronomical Society meeting in National Harbor, just outside Washington, D.C. The uncertainty has been dropping progressively over time, while the value has not been changing very much. To calculate the Hubble constant, Professor Rees and others use the cosmic ladder approach, which relies on known quantities, so-called standard candles such as the brightness of certain types of supernova, to calibrate distances across space. However, a different approach uses a combination of the afterglow of the Big Bang, known as the cosmic microwave background (CMB), as measured by the Planck spacecraft, and a cosmological model known as lambda-CDM. The Hubble constant obtained using these data is 66.9 km per second per megaparsec. A megaparsec is 3.26 million light-years, so it follows that cosmic expansion increases by 66.9 km/s for every 3.26 million light-years we look further out into space. The gap between the two is now at a confidence level of about 3.4 sigma. The sigma level describes the probability that a particular finding is not down to chance. For example, 3 sigma is often described as the equivalent of repeatedly tossing a coin and getting 9 heads in a row. A level of 5 sigma is usually considered the threshold for claiming a discovery. However, Professor Rees said that at the 3 sigma level this starts to get pretty serious, I would say. In fact, in both cases of measurements, these are very mature measurements. Both projects have done their utmost to reduce systematic errors, he added. Indeed, a recent measurement of time delays in quasars that is completely independent of the cosmic distance ladder data gets very similar results to Professor Rees' late universe Hubble constant. For the early universe, a 2017 analysis using the density of baryonic normal matter in the cosmos yields a very similar value as the one obtained by the Planck team. What this all suggested, he said, was that the universe is now expanding 9% faster than expected based on the data, a result he described as remarkable. A new physics phenomena. One way to bridge the divide is to invoke new phenomena in physics. There are various ways to account for it, including the addition of a new particle, called a sterile neutrino, to the Standard Model, the best tested theory of particle physics. The sterile neutrino would represent the 4th type of flavor of neutrino, but while the other 3 are well known to physicists, attempts to detect a 4th with experiments have not come up with much. Another possibility is that dark energy behaves in a different way now compared with how it did in the early history of the cosmos. One promising way is if we don't have dark matter be so perfectly collisionless, but it could interact with radiation in the early universe, Professor Rees said. He has submitted a paper with his latest analysis of the Hubble constant for publication in a journal. BBC